All right, hey guys, welcome back. We just finished our Unit 0 mathematics exam. Now we actually have to start our first physics unit. The first physics unit is kinematics, which I decided to split into two parts. We're going to talk about kinematics in one dimension. So one dimension would either be maybe a ball rolling on the ground, right, back and forth, or maybe a ball being thrown up in the air, but it's not doing both at the same time. So we're either on the ground or going up and down, but we're not traveling in a parabola. After we finish kinematics 1D, then we'll go into two dimensions where we have maybe you kick a ball and it travels along a parabola. That would be in two dimensions because it's moving both in the x direction and the y direction. But for now, we're just going to focus on one dimension and learning the different values for kinematics. Okay, so at the front of your notes, you have a table of all the different variables and their units. So we have time, seconds, x, meters. Displacement is change in x or change in position, which is also represented with meters. You have velocity, initial and final, which remember we could also have it represented as v naught or v0 for time 0. Velocity is meters per second. Acceleration is meters per second squared. Just the seconds is squared, not the meter. And then we also have gravitational acceleration, which for gravitational acceleration, you'll actually just see a lowercase g to represent gravity or the acceleration of gravity. But every once in a while, you'll see a formula chart that uses ag. I thought I had updated this over the summer, but I did not. We're going to use the AP Physics 1 formulas. So I will make sure whenever I write down the formulas that I use the ones from the AP Physics 1 formula chart throughout the notes. And you also should have a formula chart available to you. Okay, so maybe don't use the ones on the notes. Use the ones on the AP Physics chart. But they are the same. They just have different variables sometimes. Okay, before we can talk about motion, we have to talk about a scalar quantity versus a vector. So a scalar quantity is one that has a magnitude, but no direction given. So it only has a magnitude. There is no direction associated with a scalar quantity. Okay, with a vector, we are given not only the magnitude, but also the direction. So you have both things given. The direction is usually given with respect to the origin point and is typically noted with a positive or negative sign. Okay, but let's talk about a scalar versus vector in more detail. So if I said I walked 15 meters, 15 meters is not very descriptive. It doesn't give the direction. It doesn't say whether we're moving left or right, or maybe even we're moving north and south if it was given cardinal directions. It tells us no information. But if I said I walked 15 meters to the right from my starting position, then this has both magnitude and direction. This is a vector, and this is a scalar. A good rule of thumb is if you can point in the direction, if you can point, it is a vector. And vectors in physics are represented with arrows anyways. And so 15 meters to the right, you could draw an arrow to represent the direction it's traveling. But with scalar, we wouldn't be able to do that because we don't know what direction it's heading. Okay. Another thing, these vectors are also drawn to scale. So if I said I walked 30 meters, I wouldn't want to make that twice as long. Okay, so we do want to make sure that these vectors, it points in the direction, but it also represents the magnitude. If you increase the magnitude, make the arrow longer. If it's a smaller magnitude, make it shorter. So just be aware that the vector arrows do need to also be to scale. Okay, so scalar, no direction. Vector, we have direction. Let's talk about the different ways to represent direction. So you could say right, left, we could say up, we could say down. You could also use cardinal directions. You could say north, you could say south, you could say east and west. And the reason I have these in these two columns is because typically all of these are a positive direction. For physics, we try to standardize that. So usually most people, their right hand is dominant, so right is positive. Up just makes common sense to be positive. And then north is the same thing as going up, and east is the same thing as going to the right. All the ones in this column are associated with a negative sign. So instead of writing things out in words, you could also just say, I moved positive 15 meters and I moved negative 15 meters. Okay, and then maybe the extra context will tell you whether it's left or up or down. Okay, so we have all the different ways to represent direction. The first example we're going to give of a scalar quantity versus vector is distance versus displacement. Okay, so distance is a scalar quantity, meaning it's only going to give the magnitude and the total change in position regardless of direction. Okay, so it doesn't care if you're moving left or right or up or down. All it cares about is how much did you move. Whereas displacement is the vector version of that. So they kind of go hand in hand, but distance is scalar and displacement is the vector quantity. Okay, so with displacement, the direction as well as the magnitude are considered. You could also think about it as an overall change in position, meaning that it only considers the start and end points. Okay, and we have that in the word displacement, you have that word place. So it cares about what place you start at and what place you end at, but it doesn't really care about the path you take. Okay, let's look at this scenario. So you have a person walking around the block. He starts right here, but he also ends at the same corner. He goes 0.25 miles each leg of the block. What we need to figure out is what is the distance and then what is that displacement. Okay, so distance only cares about the total length traveled. We don't have to denote whether it was right, left, up, or down. So the total distance he traveled is 1 mile. You just add up all the sides. But displacement, what it cares about is where did he start and where did he end. Okay, so if we look at that, he starts in this corner, but he also ends in that corner. So his total position change, he actually changed position by 0 miles, which we don't even need to give a direction for because it's 0. Another way I could explain that, we just talked about what was positive and negative direction. So at first he moves down, that's negative. Then he moves right, that's positive. But then he moves up, that's positive. And then he moves left, and that's negative. So if you look at it, yes, he did move down, but then he moved up in the same exact distance. That's canceling each other out. And then he went right, but he also went left the same distance, and those two cancel out. So all of those arrows cancel each other out. You have, for every positive direction, you have the negative counterpart. And so it ends up being a total displacement of 0. Okay, this one is a bit harder example. You have this path A, B, C, D, E, F. So a little winding path. Each of the dotted lines represents 0.5 kilometers. So I'm just going to start off by measuring the lengths of each side and marking them. So A to B, that's 3 kilometers. B to C, that's 1 kilometer. C to D, that's 1.5 kilometers. E to D is 0.5 and E to F is 0.5. Okay, so if we want to know the distance, I just need to add it up. So I'm going to add up 3 plus 1 plus 1.5 plus 0.5 plus 0.5. So let's see, that's 4, 5.5, so 6.5 kilometers total. I don't need to give a direction because it's distance, that's scalar. Okay, so 6.5 kilometers, we don't care what direction. Displacement is going to be tougher. This example is a bit complex. So what I want you to do is draw a direct path from A to F because we only care about the start and the end. And I'm also going to point towards F because that is the direction he's traveling, right? It's a vector quantity, so we represent that with an arrow. All right, now I'm going to break it down into a right triangle. So if you look, you got a right-hand triangle. We have the x side and the y side, and then we have our hypotenuse. We can figure out what the actual distance of x and y are, so let me mark that. So it looks like my x side is 2 kilometers, and my y side is 1.5 kilometers. And I need to know that hypotenuse to figure out the total displacement. So that displacement, I have the hypotenuse missing, and I don't have an angle. So if you don't have an angle, you really need to use Pythagorean theorem. So I'm going to do a squared plus b squared. Doesn't matter which side is which. So I'm going to do the square root of 2 squared plus 2.5 squared. Or sorry, 1.5 squared. Oh, let me see. Oops. Messed that up. Okay, then you get 2.5 for that total side. So he did travel 2.5 kilometers. That was his displacement, but I need to give a direction with that, right? We changed position by 2.5 kilometers, but what direction do we do to change that position? So if it's asking for direction in physics, that's really asking for the angle. This is my, A is my starting point, so I'm going to mark this as the angle heading towards F. If I can figure out that angle, then I can figure out what direction he's traveling in. Okay, so the sides that I know, well, I know all three sides, but originally I just had the adjacent and opposite. So adjacent, opposite, let's use tangent. So I'm going to do tan of the angle equals, opposite side is 1.5, adjacent was 2. I do need to solve for that angle, so I do need to move tangent to the other side. Remember, when tangent moves over, it becomes inverse tangent. Okay, so I'm actually going to do inverse tangent of 1.5 divided by 2. And I got 36.87. And let's also attach a cardinal direction to that, because I still don't know what direction it is. I just know it's 36 degrees from the horizontal. So let's look at our cardinal directions. I'm going to take this vector from A to F and sketch it on the cardinal map. So if I look at my cardinal directions, it's closer to the east, but it skews towards the north. So if it skews north and the primary direction is east, that would be north of east. Okay, so to sum it all up, the displacement is 2.5 kilometers at 36.87 degrees north of east. So since this was at an angle, it made it more complex. I couldn't just say right or left or up or down. I had to give a specific angle, and I also had to give a specific direction for that angle. So that's why that example was harder. Okay, let's do some easy example. A ball rolls 5 meters north. Remember, distance doesn't care about direction, so distance 5 meters. But for displacement, we want to consider direction and mark that. Remember, north was positive, so positive 5 meters would be the displacement. The only difference is denoting the direction. A cat runs 8 meters west. Distance doesn't care about the west, but displacement does, and west is negative. Okay, a bird flies 5 meters north and then turns around and flies 7 meters south. And I did draw it to scale so I could kind of see what's going on. Now, distance just cares about the total path. So let's do 5 plus 7, which would give me 12 meters. But the displacement, we care about the total change in position. So looking at start to end, we are 2 meters south of where we began, or down. So I'm going to do negative 2 meters. Another way to think about it is this was positive 5 and this was a negative 7. So positive 5 minus 7 would give you negative 2 if you don't like visuals. Okay, let's look at a graph of displacement versus time. A good thing to know is that the origin should be your starting point. And anything in the positive quadrant just means you're to the right of the start. It could also mean up from the starting position, right? Right and up are both positive. If you're in the negative quadrant, that means you're to the left of the start. Okay, so just visualize it in your head. Maybe picture an X on the floor. That's your starting position. Okay, so at time 0, we're on that X on the floor. It looks like for the first second, I'm going to head right. And then once I reach the 5-meter mark, I'm going to stop for 1 second, 1 to 2. Okay. Then it looks like I start to head back to my starting position. So if I'm going to head back to my starting position, picture the person pivoting to the left. We're going to head left. Oh, spelled head wrong. We're going to head left back to that X on the floor. We pass by the X and we keep going to the left until we hit 3 meters from the starting point. -3 means we're 3 meters to the left of where we started on that X on the floor. Then we're going to stop at that 3-meter mark. Then we're going to head back right. So every time we change from a negative slope to a positive slope, that's changing direction. We're going to head right. We pass by our starting position again, and then we stop at 1 meter to the right. That's where we stop. Okay, so try to run through that in your head. Anytime you have a flat line, that means you're stopped in place. If you have a positive slope, that means you're heading to the right. If you have a negative slope, that means you're heading to the left. Okay, so let's answer the questions. During what time period did it stop moving? It stopped moving from 1 to 2 seconds, and it stopped moving from 4 to 5 seconds. At what distance from the origin did the object stop? Well, let's give it 2 answers because we have 2 times that it stopped. So the first time it stopped, it was 5 meters, let's say +5. That was from 1 to 2 seconds. And then the next time it stopped, it was -3 meters. And that was at the 4 to 5 second mark. Okay, so we started 5 meters to the right and we stopped 3 meters to the left. At what time interval is the object to the left of the origin? So remember, the x-axis is kind of the origin or the starting point. So it looks like from time 3 to about 5.8, we were to the left of that starting position. 5.8 is a guesstimate, so if you said something different, that's fine. Okay, this next example would not happen in real life, but it's a good way to think about distance versus displacement. So Bill gets into his car and drives his wife Hilda to the JFK airport. Hilda boards a flight to the Boston Logan airport and arrives there several hours before Bill arrives by car. So they drive to one airport together. The wife flies, but the husband drives, and they end up at the same place. Okay, so greatest displacement, remember displacement is start and end. So if they start at the same airport and end at the other airport, they both have the same displacement. Okay, but let's think about direction, distance. Which with distance, you kind of have to think about the logistics of a plane versus car, right? The plane can fly in a straight path. They have open airspace, but the car has to go through like curves and valleys and hills. So if we're thinking about the greatest distance, Bill is probably going to go the greatest because he's going by car. Okay, whereas the plane can fly in a straight path. All right, just like distance and displacement is scalar versus vector, there's another one for speed. Okay, so speed is the scalar version. So let's say you're driving in your car at 70 miles per hour. That tells me how fast you were going, but that doesn't tell me what direction. Okay. But velocity, which is what we use in physics mostly, velocity is a vector quantity. Okay, so it is the change in displacement over a given period of time. Okay, Unlike speed, velocity can be negative or positive because we're talking about direction with velocity. And just like before, right or up should be positive, and left or down should be a negative velocity. Okay, so if they're traveling to the right, it's going to be positive. If they're traveling to the left, it's going to be negative. And you could also use cardinal. North and east are positive, west and south are negative. Okay. All right, so let's look at the formula for velocity. So the formula for velocity is change in position over change in time. Remember that delta does mean change. Another way to write it is the final position minus initial position over over the total time, right? This also closely matches the slope formula, right? The slope formula is change in y over change in x. The reason why I bring up the slope formula is because you could actually use, in graphing, you can use the position versus time graph to find velocity. If you have position and you have time and they're being divided like that, then that means to analyze the slope. And we kind of talked about that in our math unit. Okay, so if I can find the slope of this line, it would be the velocity, because it's change in position over change in time, change in y over change in x. All right, let's look at this descriptive graph off to the side. So it says in the first part, A to B of the graph, the object is moving with a constant velocity. So from A to B, we do have a slope, but it is a linear line. So anytime you have a linear slope, we associate that with constant velocity. So it's not speeding up, it's not slowing down, it's going the same speed the whole time. But on a distance versus time graph, if it's a flat line, that means it's stopped, right? And if we're stopped, then that means that the velocity should be 0. And it says that the object is at rest, not moving. So our velocity must be 0. Then it says in the third part, C to D, the object is again moving with a constant velocity back to where it started. Okay, so again, we have a linear slope. Linear slope means it's constant, but we'll be heading towards the left, so that slope is negative. So we have a negative slope right here. That means it should be going to the left, back where it began. Positive slope at the beginning means it was heading to the right. Okay, so just to recap, from A to B, it's heading to the right at a constant speed, then it stops, and then it pivots and it heads left with a constant speed back to where it started. Okay, let's try to use the formula to solve this next problem. So an alien spaceship is 500 meters above the ground and moving at a constant velocity of 150 meters per second upwards. How high above the ground is the ship after 5 seconds? So the first thing I like to do is actually look at what the question is asking. How high above the ground is the ship after the 5 seconds? So height is more of a position. We could call it y this time, or you can call it x, okay? Since it's moving up and down, it's better to call it y instead of x. X is along the ground. It says how high above the ground is the ship after 5 seconds. So this is going to be after time has passed. So I'm going to call it the height and final, YF. Okay. Now let's look at the constant velocity. So 150 meters per second upwards means positive 150 meters per second. Up is a positive velocity. And then the first piece of information it says is an alien spaceship is 500 meters above the ground at the start. So let's call that the first position, y0 at time 0. Okay, so let's start plugging things into our formula. On the AP Physics exam, they'll often ask you to derive an equation, but they won't ask you to actually plug in the numbers. So we're going to derive the equation, but we're not going to plug in our numbers till the very end. Okay, so we have V. I'm going to use Y because we are talking about going up and down. Okay. Let's go ahead and write that out longer. So we have velocity equals Change in y would be yf minus y naught. And then change in time, we're starting at time 0, so usually change in time is really just going to be written as t. Okay, so now that I have all my variables, let me go ahead and rearrange. And in this problem, yf is the question, so let's rearrange for yf. Let's take care of divided by t. So if we're dividing by t, multiply by t on both sides. Let me rewrite it up here. So we have v times t now equals yf minus y0. And last step, again, we're trying to isolate yf. So if we're subtracting by y naught, we're going to add y naught to both sides. And so my final equation is v times t plus y naught, and that should give me yf. Okay, so on the physics exam, if they were asking you to derive an expression for the final position, this would be your final answer. Deriving doesn't involve any numbers, but I have numbers, so let's go ahead and plug them in. So go in order. Velocity is first, which we said was positive 150. Time, 5 seconds, plus 500 equals, and let's type that in because I don't have YF. Okay, and then you get 1,250 meters, and that's the final answer. Okay, so I would practice whenever you're doing physics, deriving the expression without numbers, and then plugging in numbers after the fact. All right, so let's look at these graphs. We just did an equation, let's talk about graphing. So let's look at a position versus time graph, which we talked about in the previous lesson. Position versus time. If it's a flat line, what does that mean about it? Well, it means that the object stopped. If the object is stopped, what does that mean about its speed? It means that the speed or velocity should be 0 meters per second because it's not moving. Okay, so let's write ourselves a note. If flat line, or if your technical slope is 0, then the velocity should equal 0 meters per second because the object is stopped. Okay, so when you see a flat line, automatically know that velocity is 0 on a position versus time graph. Okay, the next position versus time, we have a positive slope that's constant or linear. Okay, so if it's a positive slope, that should mean it's traveling to the right. And if it's constant, that means it's not speeding up and it's not slowing down. It's going at consistent speed. So positive slope should be traveling right. Since it's linear and straight, it means it's constant. Okay, so I can't actually get a numerical value for velocity, but it should be a positive velocity that doesn't change. Okay. Let's look at this next one. So we have a positive slope, so it should be heading to the right, but we also have a curvature. Let's look at the curvature. It gets steeper over time, so the slope is increasing. And remember that on a position versus time graph, the slope is the velocity. So if your slope is increasing over time, your velocity is increasing over time. Okay, so positive slope means it's heading to the right. And then the curve with an increasing slope means velocity is increasing. Okay, so velocity is positive, but it's also increasing over time. Okay, let me show you what it looks like if it slows down. So on a position versus time, if it's slowing down over time, it should be like a plateaued curve. Because at first she's going really quickly, the slope is steep, and then it slows down into a flat line to where it comes to a stop at the end, right? Once it's flat, it's stopped. Okay, so positive slope, but it's also a decreasing slope. Okay, so positive slope means she's heading right. But that decreasing slope, the decreasing value of the slope, means that the velocity is decreasing or the object is slowing down. Okay, so she's heading right, but she's slowing down. All right, we're actually gonna skip this example. Let's look at the next concept. So this is another position versus time graph. But there's kind of two ways they can ask about velocity. They could ask you for the average velocity, or they can ask you for the instantaneous velocity. Okay, the average velocity is the overall, how fast was she going? And instantaneous is at a certain time. In that moment, what was she doing? Okay. So the average velocity is the change in position over change in time when it occurred. And the instantaneous velocity, it tells you the speed and direction of an object at a specific instance in time. Okay, so on a position versus time graph, if you take the slope at a very particular time, it's also known as the tangent of that line. Okay, so you're looking at very specific value. Okay, so let's look at this part. What is the average velocity from 0 to 10 seconds? So it wants the total graph. Okay, so change of velocity is going to be change in position over change in time, or final minus initial, right? So let's look at position. Final position is 25 minus 0 because she started at 0. And then change in time, we're talking about 10 seconds to 0 seconds. Okay, so 25 over 10. Looks like her average speed is 25 meters per second. Okay. The very next question asks what is the average velocity again, but this time it only wants you to do from 0 to 5 seconds. Okay, so it really wants the velocity from 0 to 5. Doesn't care after 5 seconds. So let's do that. So change in x over change in time. Final position at 5 seconds is also 25 meters. Minus 0. And then the time change is just 5 seconds this time. Okay, so it looks like after 5 seconds, you see how it stopped? It's a flat line. That was actually hindering our overall average velocity. So our average velocity should be faster from 0 to 5 because she traveled 25 meters in that 5 seconds. Okay, so that's 5 meters per second. So double the velocity of the overall graph. Okay, let's look at instantaneous velocity. So it'll tell you a time. It wants to know the exact speed at 3 seconds. Well, speed, you still have to find the slope. Okay, the slope at that particular point. But if you notice, the slope at that point is the same as the slope all along from 0 to 5. So the instantaneous velocity at that time should be 5 meters per second because she was traveling that speed consistently all the way through. It was the same slope. Okay, so if her slope is not changing, it's the same speed that whole section of time. Okay, if I ask you what is the instantaneous velocity at 9 seconds, well, I would look at that slope at 9 seconds. Her velocity is 0 because the slope is flat, right? So you just look at that particular point and look at that slope in that time. All right, let's try to draw some position versus time and velocity versus time, which I probably should have used an X for that. Okay, so a ball sits motionless on the table, so it's not even moving at all, and it's right at its starting position. So I'm just going to draw a flat line right on the x-axis. What would the velocity look like? Well, if it's a flat slope of 0, then the velocity is 0. We always just look at the slope. So for the velocity, I want to draw that as 0 as well. Okay, a man starts at location 5 meters north, so we should be positive 5. He stands there for 3 seconds, so if he's standing there, that should be flat. Okay, and then he walks away from his house So he's already 5 meters north. He walks further away. He should continue north with a constant speed. So constant speed should be a linear slope of 1 meter per second. So 1 meter per second, that should be the value of the slope. Okay, so let's draw that. He starts 5 meters north. He stands there for 3 seconds. So I'm just going to draw a flat line. Then he travels away from his house, so he should be going more north at a constant speed of 1 meter per second. Okay, so I'm going to draw a straight linear slope. And, there's not very many numbers involved with this graph, so I don't know for sure if it represents 1 meter per second, but it is traveling the direction it should at a constant speed, which is the linear slope. Okay, so let's look at the slopes of these lines. From 0 to 3 seconds, that slope was 0. So at this point, the velocity should be 0. We're always just looking at the slope. So for the first 3 seconds on our velocity graph, we want to draw it at time 0. The velocity should be 0. So we're going to draw it on the axis for the first 3 seconds. Then my slope is positive because he's heading more north. So my velocity should turn positive, and that should be an instantaneous change. So kind of draw like a stair step. And it said in the problem that it should be 1 meter per second that she's traveling. So I'm going to mark it. Okay. But again, I put it in the positive quadrant because that slope is heading more north, and north is a positive direction. Okay. All right. A dog starts 6 meters west. So west was a negative direction. He runs towards his house. So he should be heading back to the axis. With a constant speed of 2 meters per second. So constant speed, we're going to draw a linear slope. No curves. And he continues to run by his house, so go by the axis for another 5 seconds, and then he stops. So stop should be a flat line. Okay, so let's kind of draw that. So 6 meters west, so we're down here at the start. So we're going to start right here. Then he runs towards his house with a constant speed, but he continues running by his house for 5 seconds, and then he stops. Okay. So again, we're not putting numbers down. We're kind of getting the general shape. All right. So let's look at the slope so we can change it into a velocity graph. So at the beginning, the slope is positive. And so I want to make my velocity positive, but it's also constant. Okay, so my velocity should be positive, but it should be constant. So we should see a flat line. Then he comes to a stop. And when he comes to a stop, my slope is 0. So my velocity should be 0. So immediately on that velocity graph, you're going to go down to 0. And then you're going to mark it for the rest of the time. Okay, let's look at this next one. A woman leaves her house riding her bike north at a constant velocity of 3 meters per second. So she leaves her house. We should start at the origin. She rides her bike north at a constant velocity, so we should do a linear line. After 5 seconds, she gradually slows down, so we should have a decreasing slope. Until at 15 seconds, she completely stops, so then we should turn into a flat line, which since it's already a gradually decreasing, it should just naturally turn into a flat plateau. Okay, so let's start at our origin. She rides her bike north, so we should do north at a constant velocity. So we should have a linear slope going north. Then at 5 seconds, she gradually slows down. So I'm going to start curving downwards, and then we reach a stop. We have that flat line. Okay, so we go straight for a little bit. Then we start curving, and then we eventually go flat. So something like that. Okay, so while the slope is positive and it should be constant for a while. Then it decreases at this point. So we should start going to 0. And then at the flat point at the very end, the slope is 0. So what that looks like on the velocity graph, we're going to start positive and constant. Then when she starts slowing down, we should gradually head towards the origin axis. And then at the very end, she stops. So she reaches 0 and she stays stopped. Okay, we'll stop right here and then we'll pick up on acceleration and how to go from position versus time to velocity versus time to acceleration versus time. Okay, so that's it for right now, and I'll post the next video soon.